Good afternoon, everyone. My name is Tien-Yin on behalf of Taiwan Space Union. I'm very happy to introduce to you the fourth lecture by the TSU, the Taiwan Space Union, the GIS online program. I did the first three lectures about the GIS concept and some application, and also about the smart city application. And last week, I just finished one of logistic and transportation issues by the GIS and remote sensing. So this week, the course will talk about the data analysis and data cubes in the GIS and remote sensing. It will be hosted by one of my colleagues. He's a very young professor in Fengjia University, the Dr. Hao. His name is Chen-Yu Hao. So his interest has several different aspects, especially he's doing a lot of different kind of research regarding the Open Geospatial Consortium with the geo database, and also how to smartly use those kind of images to identify lots of different kind of issues and use of the GIS. He graduated from Fengjia University, got his bachelor degree, master degree, and also a PhD degree from the GIS program in the Fengjia University. So let's welcome the Professor Hao Zhenyu for his lecture this afternoon. Hope you're enjoying the 2-hour lecture regarding the data analysis and data cubes in GIS and remote sensing. So, okay, it's your stage, Dr. Hao.
Okay, thank you. Let me share my screen.
Yeah, very good. So it looks very clear, and yeah, you're on the stage now. Thank you.
Okay, thank you, Professor Jimmy. All right. Hello, everyone. I'm Hao from Fengjia University, and it is my pleasure to be here as the speaker for this session. And as Jimmy mentioned, I also come from Fengjia University and currently working at the GIS Research Center. And I'm in this position for approximately 15 years. During this time, I've been involved in various projects implementing international standard for different kind of spatial information. And today I'm going to talk about the data analysis and data cube in GIS and remote sensing. So the topic of data cube is particularly intriguing, and it's an area I've had the opportunity to dive into the international stage. And I look forward to sharing some experience with you during we have like approximately like 2 hours. And again, thank you for having me. And let's dive into this topic. So I believe you saw this slide before, and I want to bring this up again. There is a question for you as we go through the presentation. Where is the data come from? Okay, so currently the Earth's observation encompasses various scale, ranging from top tier, the satellite, and a lot of micro satellite, the CubeSat. And we have high altitude balloons, the aerial vehicles, the UAV, the drones, and also to ground-based sensors. So through remote sensing technologies, we can obtain specific target feature from these diverse sources. And for okay, so so nowadays with the advancement of hardware technology and some affordable price, so over 1 million satellite images are captured and downloaded to ground station every day. So, in addition to that, more than 500 zettabyte data are generated annually for all types of sensor. So, the days of struggling with lack of data for research and are eliminated. Instead, we are now facing the challenge of managing the explosive growth of data. So in the era of abundant data, the key line is in efficiently identifying data suitable for our analysis from the vast pool. We also need to employ appropriate data referred to as analysis-ready data and utilize the right tool or platform for analysis as we dealing with Earth observation field research. Okay, so uh, from this slide, I noticed that Jimmy also used this slide in previous lecture, but I think it's evident that our planet is surrounded by a multitude of satellites. Moreover, countries and technologies company and some big tech companies worldwide continue to launch more into orbit. So these satellites serve various purposes extending beyond communication and military functions, whether they are for the meteorology or Earth observation, they play distinct role in gathering environmental information about our planet. And here's some applications that we have carried in the past few decades. So once we acquire this kind of satellite image, a wide range of remote sensing analysis and research can be conducted. And in this particular image, we are examining the changes in the Chaoling area, which is located in the middle of Taiwan, in Nantou County. And the material is from Spot satellite, which was launched and operated by a French company. The comparison focus on the alteration in landslide before and after the we call 921, which is a very large earthquake that happened in Taiwan 20 years ago. And through the visual inspection, we can intuitively observe extensive landslide occurrence in the region after the earthquake, right? In a right picture, and also the same applications that in this image we also use spot satellite image that to compare the impact of typhoon Mingduli, which is also a very serious typhoon that invaded Taiwan in 2004. And before and after the typhoon invasion, the focus is on the area affected by the debris flow in Songhe community, which is also located in Nantou County along the Daja River. Okay, so this is another application that remote sensing can be adopted for the detection of marine oil pollution, which is happened quite often recently. And this oil spill incident involving a Greek cargo called Amargos, which ran aground near Kending National Park in 2001. And this incident resulted in a significant release of fuel oil, causing pollution in the nearby ecological conservation area. And except the visual inspection, We can also use remote sensing analysis techniques such as the image classification and some image recognition. So we can pre-process the image and classify the land cover type to identify specific land uses. And the example here, we can employ image from the image we used from was from Taiwan self-launched satellite, so-called Formosa Sat 2. So we use the Formosa Sat 2 image to identify the cultivated area of rice field, which is the yellow polygon. And this information can be crucial for regulatory authority in compensation or yield calculation purposes. And the bottom image shows a rapid acquisition of vegetation cover condition in a national park through the image classification. Okay, so here are some further steps. The multispectral feature within the image, when combined with other administrative layers such as cadastral data, can assist us uh, to distinguish different crops and effectively managing them through some web technology and databases. All right, so this is a project that we carried several years ago. And this workflow, we integrate the web GIS technology to enable general user to use their browser to access to some satellite image, so the user can access conveniently uh, for searching suitable image online. And also user can customize parameters for specific image, like the right hand area. And the user can also adjust features such as the contrast, transparency, and intensity of the image. And we also refer to these uh, capabilities as online image enhancement. Okay, so this is a video uh, that that's recorded from a project that we carried a few years ago as well. And this video shows that user can perform an online editing and mapping function directly on the original images. And this includes tasks such as comparing aerial-based map with ground features, extracting specific objects, and setting some point of interest, switching base map, and more. So through the integration of GIS and remote sensing, in this manner, user can enhance the of efficiency to their image analysis task. So these are all some example about the practical usage uh, of remote sensing data. And in the following few slides, I want to borrow some result that we carried in OGC testbed. So this testbed uh, is a collaboration project that we have participants. And this layer address that when we integrate satellite and aerial photo for object detection, uh, that adopt OGC standards. So we apply machine learning or deep learning technologies to analyze the data at different scales. So you can see there's three different scale. The first is the high resolution optical satellite imagery, and the middle resolution is radar or optical or some middle resolution optical imagery. And and as well as the ground level IoT devices. So we apply these data sources for object recognition, change detection, and real-time event monitoring, and some target identification. So um, these studies meant to find or collect different resolution data resource, and this is the Pleiades. It's an environment focused constellation. So also from France. So which launched in 2011, and the constellation is remain operational. So we collect the image and put that into machine learning algorithm as well. And this is the radar set. The radar set 2 is a Canadian space. It's from Canadian Space Agency. It's an Earth observation satellite, and radar imagery is a technology based on active sensing. Well, it has lower spatial resolution, but it's less affected by weather conditions such as cloud and haze compared to other passive sensing technology. And this is the ice eye, which is also a SAR image that we collect in this test bed. And for the most detailed camera videos, common dynamic image recognition algorithm like YOLO can be deployed to identify the object, and such as vehicles. So regarding to these three scale of data, the high resolution, the middle resolution, and the ground cameras, the the primary goal of the OGC testbed is to explore how geospatial standard can be applied in these analysis processes. And this include crucial aspects such as ground truth data for image classification, the training samples for AI training, the algorithm interface, the application interfaces, and more, especially when dealing with the image classification. So so you can see this is an image that indicate the observation of from different scale. There's still a question of wording. So in this case, for the same object, it may be recorded in completely different form in image of different scale. From the ground scale, we can recognize this is a white lorry uh, clearly, but from an aerial image or a satellite image, um, a white lorry cannot be easily distinguished or recognized, and present similar or appear similar to a minivan. So how to determine these two objects are the same object become a very tough issue, right? And how to discerning the size of the object in different image can also be challenging. So that's just the remaining questions, because nowadays we still can get the object information from various remote sensing uh, device or payload. Okay, so this is just an example that we can use AI to analyze our remote sensing data. So certainly, in addition to challenge, AI has been widely used, right? And in this slide, it showcased that Taiwanese government used AI on CCTV camera that installed on the street. So by implementing a model for detecting road flooding, the system can determine the extent of flooded area, and moreover, uh, this information this information can be integrated with some web GIS, some IoT and 3D GIS technology. And like you see, this is a 3D city mesh that we can measure the flood area and display on the 3D WebGIS platform. So which means we can create a relatively digital twins on the based on the ground information. Okay. All right. So here's a here is a activity that's completely anonymous. So I want you to share a few keywords based on your past experience regarding to practical challenges encountered in remote sensing image process or analysis. So any keyword will be fine if you have no idea, or you can put just UAV, or is the price expensive, or hard to get the data, and so on. Everything are welcome. So I give you 3 minutes, and I can share the result here. Just make sure everyone can see the QR code, right? Okay, I already see some response. Yes, yes. So yes, as I know, most of the students or audience you are from profession remote sensing field. So yeah, like uh, still some people mentioned about lack of analyzing skill and um, the the satellite image is quite expensive if you want to purchase a large area. And there is some vector data, some unfamiliar algorithm, some raster data masking, okay, and 3D topographic. Okay, these are all the remote sensing issues that we when we dealing with the data. Okay, great. Then we have more large amount of data. Exactly. Yeah, because generally most of the remote sensing data they are stored in raster format, and the raster data is quite uh, expensive to store, right? And okay, the analytical skill, the pre-processing, comprehensive, and some quick. Okay, and the remote sensing knowledge. Okay, okay, great. Thank you for your response. And as I mentioned, that we also, as everyone mentioned, we're also facing similar issues. So from various topics that we discussed earlier, uh, we can observe that the processes of image acquisition, the pre-processing, exchange, and while this process not contributing directly to scientific research, but it did consume a significant time and effort, right? So in Taiwan, the remote sensing image are typically acquired by environmental management authorities and applied to different issues such as the forest degradation, the landslide monitoring, the crop management, and some cultural heritage preservation and water quality analysis. So Taiwan also processes domestically launched Formosa series data, and as a result, the relevant data is peer across various agencies, is managed across various agencies, like TASA, the Taiwan Space Agency, the Environmental Protection Agency, the Agricultural Department, Water Resource Agency, and a lot of local governments. So they produce the satellite imagery, the aerial photos, and UAV images independently based on their some operational need. And due to the characteristic of Earth observation data, it is commonly stored in raster format, like some of you mentioned. While some format, the raster format offer simplicity and easy and general uh, in analysis process, but they may lack efficiency in terms of store management. So consequently, different government agencies and research institutions are not only invest considerable resource in collecting and purchase image data, but also facing challenge on how to store and how to share those kind of data, right? And and in the in this topic, Taiwan has started to prioritize the application and analysis of data cubes, emphasizing the concept of image data warehouses. So the goal is to address issues stemming from the abundant of image sources and their storage. So additionally, efforts are being made to reduce the time spent on accurate and accessible image search and preprocessing. And furthermore, there is a focus on exploring different skills and method for image analysis. So this need have lead the consideration of implementing DataCube software. Okay, so we already talked about the applications, but what is the DataCube softwares? So for a comprehensive DataCube software suite, it must encompass several key features. So first, it should support temporal and multidimensional analysis. That's the must part. So currently, two prominent options globally are Open Data Cube and Rasterman, representing open source and commercial software respectively. And second, the software should offer a wealth of analysis-ready data, which means when analyzer, they don't need to spend a lot of time to do the pre-processing work like the radiation correction, the geometry corrections. They can just jump into uh, the image analysis stage directly. So with a wealth of analysis-ready data can streamline the data collection process for researchers. And this ensure the data is ready for immediate and analysis without extensive preprocessing. So additionally, support for open standard is also very crucial for interoperability and seamless integration with various tools and platforms. So the software should facilitate open standard to promote which can promote the data sharing and collaborations. So the last one will be the ability scientific to provide specific interoperability features and support for the integration of new application is also essential. And also, this ensure the software remain adaptable and to involving research need and can accommodate the integration of emerging technologies. And next, I will use a few cases to introduce the scenario in Taiwan where data cube can be applied. As you can see, Taiwan faces constraint in agricultural development. We have two-thirds of the land is mountain area, and which also indicate a complex and diverse environment, not just ecological environment, but also the very complex topologies. So uh, on the left hand side, we have only 8,000 kilometer square uh, uh, of land that's suitable for cultivation and accounting for just like 23% of the entire country. And notably, uh, most of these agricultural land are already inhabited. Inhabited. That means not all uh, land that's suitable for cultivation can be applied as farm. So so Taiwan's farmland are mostly small, average less than 1.1 hectares, with an average farmer age of 62. That's highlights an aging farming population with a significant number of small size farmers. So in terms of weather, Taiwan experiences a subtropical climate with abundant rainfall, high temperatures, and humidity. Additionally, the island is it's suffering to typhoon impact almost every year. So I brought this background to let the audience know that the agricultural environment and challenges in Taiwan. And, and similar to many Asian countries, the annual heavy rainfall and frequent typhoon in Taiwan often result in flood and wind disaster and various challenge, which cause various challenges for the farmers. And also, the composition of small-scale farming contribute to a high sensitivity in the prices of many different kind of agricultural products. So the waving vegetable prices experiencing sudden surge and decline can lead to some public protest. And in some extreme cases, such as price collapse, the government may need to compensate the farmer and provide subsidy to support them. Okay, so uh, this this image illustrate the this image illustrate our application of the data cube concept. analyzing the NDVI variation of cabbage at different growth stage. So this analysis enables us to predict the cabbage yield 90 days later, serving as a basis for providing planting recommendations to farmer. So for instance, we can advise farmer to consider to switch to other crops based on the predictive data. So this is a very similar research that utilize satellite image to access to the phenology of pineapple based on the BBCH scale, which is the growth system that of planet, and it reveal distinct characteristic of pineapples at different stage through NDVI features, and the temporal analysis allows for a better understanding and management of pineapple yield variation. And this is a research topic that conducted by a professor from University of Michigan. It analyzed the vitality and expected yield of sugarcane field in Mozambique using a very detailed data, the daily NDVI data over 2 years. So the concept is also incorporate temporal analysis through the use of data cube. So here's another common challenge facing Taiwan and Southeast Asian countries, the natural disaster. So Taiwan also experiences approximately 6 to 7 typhoons each year, and accompany factors like landslide and debris flow triggered by typhoon and earthquake often result in significant loss of life and properties. So this is some real video that recorded by the Taiwan media. And this research was conducted by Taiwan Forestry Research Institution, and they collect the data from Open Data Cube, which is the open source version of the data cube. So it involved extracting 355 Landsat 7 or 8 images from the Open Data Cube software, and spanning a period of 70 years from 2000 to 2017. So furthermore, this study involves the exclusion of 285 cloudy images and remaining a subset of 70 cloud-free image for the from the original data set. And here's some basic analysis or preliminary analysis that of that 355 images. So among those images, there's only approximately 20% are classified as cloud-free images. So the analysis indicates that the month of February from January to September have higher probability of cloud-free condition, right? Which is a little bit obey the institute of people, but that's the statistic data, and we they overlay this image, and creating an animation reveals the extent of riverbank exposure. When comparing the NDVI values and notable observation in is that the same region of the of eastern Taiwan, there was a significant decrease in vegetation after the impact of Typhoon Morak in 2009. So, with post disaster recovery and management effort, the vegetation significantly recovered to its pre-disaster state by 2005, around 2015. So, if we categorizing the river into upper, middle, and lower stream, that based on the depth of greenery, we can compute the NDVI for each cross section over the years, and a deeper shade of green indicate more vegetation cover. And in the result, we can observe that the upper area, the upper string from A to B, uh, shows minimal increase in exposed land over time. But in contrast, the cross section and the downstream area from G to H that experienced a significant reduction in vegetation covered around the year of 2009. So this is some analysis that if we can acquire a large amount of time series data. So if we want to analyze a large amount of data, it will require higher higher the better infrastructure, um, and also a more comprehensive research plan. So in 2017, the National Center for High Performance Computing, the NCHC, have been supporting the National Infrastructure Plan, and they try to leveraging existing research and development capability to enhance to facilitate the vibration application of no matter AI or cloud technology in Taiwanese industry. And to achieve this, the uh, the NCHC is trying to solve the main issue of the large amount of data analysis, the remote sensing data analysis, which is uh, there's some they try to create like the time series image querying safely, secure data sharing process, and try to reduce the duplicate purchase or investment on the remote sensing data, and also to solve the issues on the storage cost. So the main purpose is try to build a Taiwan national raster data repository. Okay, I think it's about time to break. We'll have 10-minute break. We're back on 3 p.m. Okay. All right. Let's keep moving on to the topic regarding to the data cube infrastructure that we accomplished in Taiwan during recent years. Okay, so as I mentioned, this infrastructure is based on NCHC infrastructure The NCC standard for National Center for High Performance Computing. They have the most comprehensive cloud computing and network infrastructure through the entire Taiwan. This includes the establishment of Taiwan National Research and Education Network, the TAOREN, and the series of supercomputers. The integration of DataCube with supercomputers infrastructure make make this idea possible to move on to move DataCube to the cloud and offer its services to public and industrial sectors. And oops, and this is the idea that we propose uh, to the public sector. This concept, so called GIS, is a service that's integrating the data cube and 3D platform into the NCHC supercomputer through a cloud architecture, which made the GIS, the data cube and 3D platform become kind of platform as a service. So this provide a service framework that's similar to SOS and to POS, allowing regular user to access and utilize DataCube's functionalities without the need to set up their own DataCube instance. So the public sector just need to rent a resource, then uh, they can access and they can use the capability from these two software. And in based on the architecture, we adopt a German software we call Rasterman, which is a commercial software uh, as our core of our DataCube service. And we have been progressively importing various images into DataCube and testing the performance of Rasaman as well as its overall support for OGC service. So from the architecture, you can see the Rastaman has its own REST server which can manipulate with file-based image or database resource. And for the output, they can support the OGC standards such as the web coverage service, the web processing service, and the web map service. And if you want to do some advanced calculation. They also support the web coverage processing service, which can allow you to process the image on the fly. And this is the some experiment that we conduct to validate the development of a simple user interface for quick access and display image with DataCube. So it's just a very simple process. The user can select an area as the bounding box query condition. Then it will send to the backend uh, to access the image. That's it. That's uh, appears to be feasible. Then this is another experiment by utilizing the pre-processed NDVI style. So user can also Swift query specified time and NDVI image, enhancing the efficiency of the retrieval processes. So the user in the experiment, we use the rapid eye image as the test image, and user just need to click the NDVI button. They can the system will display uh, the NDVI result, and also there's a statistical result, uh, which we can get the maximum, the minimum, and some other preliminary statistic number of the entire image, and create a statistic graph in a very efficient way. And and based on the experiment that we conduct in the past few years, the final concept is the national data cube, with the goal of establishing it within the NCHC environment. And this platform aims to allow different government agencies to upload their data to DataCube, and the DataCube will then provide a basic querying, analysis, and cloud computing services to all the user that register to the cloud system. And furthermore, the related services should be compatible with common or standard software, such as the Content GIS, the Esri, the ArcGIS, and other web map libraries which support open standards. And and once we confirm the concept of the national data cube, the next will be design the detailed technology architecture. So the overall architecture adopts a microservice approach, which we use container as our main structure. So where all programs utilize Docker uh, uh, as the underlying environment, you can say that. And this choice not only ensure the cross-platform capability, but also provide rapid and automated deployment capability, which is important because it's a cloud-based software, and we also provide some cloud services to different sectors. So it's need to be set up or shut down in depends on the usage. So the Docker can help us to manage the real usage and without wasting some other resource. So, and last one, by integrating with external AWS S3 for extensive storage space, the cost of the data access can be minimized uh, to acceptable or affordable level. Okay, then at the same time, we also test the integration process between DataCube and some other AI models. In this case, we use TensorFlow to build a crop recognition model and attempt to dynamically extract and analyze data from data cubes. So this is the process. Uh, this process reveals with Rastaman as the core, providing the data access interface, and the machine learning code is responsible for communicating with harassment to to obtain the data. And there's a web user interface on the other hand, offer users the capability to input time and spatial conditions for queries and analysis. And this is the experiment demo that we carried last year. The query process in this trail involves selecting a spatial range, querying the list of intersecting image through the get capability, allowing user to preview the selected image, uh, and 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 also user can trigger the machine learning code by clicking the analysis button to communicate with Resume. And once it retrieves the data, it will display the boundary of a specific field uh, on the WebGIS map. And this trail support several, I think 3 to 4 various crops, such as the bananas, the betel nuts, and some others. And this is the platform that we just finished this year, and we already present that in this July uh, on the Taiwan GIS Society conference. The We call this platform the Geospatial Data Exchange Platform. You can short as the GDXP. Was as I mentioned, is launched this year in July. So currently, it supports Taiwan government agency and also research institution to upload their data by themselves once they registered an account on the platform. So through the authorization mechanism provided by the system, the user can apply for permission to download images after obtaining approval from the respective authorities. And currently, the GDXP support 4 access approaches, including the use of QGIS, the Quantum GIS, which is the open source GIS client software, and uh, and the QGIS extension, which is we developed 2 separate plugin to support our customized WCS and WCPS. The customized part is we add the authentication mechanism into the service, and also the GDXP has its own web user interface, and we also provide some custom programming access. You can use Python, Jupyter to access the data, and also the service endpoint, the OGC web services are also available online. You can write your own code to access to the software directly. And this platform we primar, primar, primarily utilize the WMS and WCS, which is the web map service and web coverage service as interfaces for communication between different user interface and the backend. And WFS can display various type of vector and grid data, and it can transform it into a format that easy to for user to browse through their browser. And this mechanism can facilitate the browsing geographical information and enhance the visualization of maps. And the other service is the WCS. We also implement the WCS that to let user query and display multidimensional coverage data, and every standard WCS has at least three core methods, which is the get capabilities to let uh, the 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 user retrieve the data catalog, and the display coverage to retrieve the metadata of a specific coverage, and the get coverage operation can let user to retrieve uh, the the, the the actual data. Okay, so for now, this is the web user interface of the geospatial data exchange platform, as I mentioned. And every registered user can access to this platform uh, and and download or access the data set. So for now, the data cube contains more than 30 coverages with 300 terabyte data set, including part of Formosa 2, Formosa 5 image, and also um, we cooperate with some professors. They put their simulation results. So we have the air pollution, the flood simulation, and weather simulation, and so on. And this is the video that of the system operation. I apologize for the Chinese language explanation in this video, but the step you can see can be roughly divided into the selecting layer, viewing and previewing images, and after confirm the service endpoint for WMS and WCS, you can add the service into QGIS by passing the provided link, and the input the specific information and token. Then you can browse that image in a QGIS. And except the web user interface, we also support the different use of QGIS extension, and also a Python library. User can obtain a personal token from the web interface, then use the token to access the authorized or open coverages. So this is just a a screenshot that to let you understand we still have other approaches. We will show some details later. And uh, from our side, we also developed an application to demo how to integrate the 3D platform and the data cube, right? Because 3D platform is also part of the NCHC GIS as a service infrastructure. So we have successfully integrated the air quality pollution that compute through artificial intelligence by a professor from Chen-Yu University. Uh, from their team, they provide a very detailed air pollution with time series data. So this system also has the time series button. Uh, you can you can switch the time frame. So it's also evident that combining data source from the data cube enables the development of innovation applications. And next, we will provide a more detailed introduction to the WCPS service within the GDXP. So currently, the GDXP offer three data cubes that are federated together with each other, and the main storing data is open data. So the data is open to all research institutions, but it will require the and uh, required to register an account on the website. So if you have interest, you can contact me. I can send you the instruction of the information. And now we are going to introduce about some detail about web coverage processing service, which is a very um, powerful service that enable user to calculate their remote sensing data on the fly. So this service is designed for analyzing and pre-processing multi-dimensional coverage data on the server side. And this include tasks such as data computation, the statistic, the image band composition, and scaling. And the goal is to provide easier access to analysis-ready data for clients. And WCPS also support various computational operations such as the aggregation, the comparison, and also it has some metadata operation and also the coverage operation like the reprojection and some other more. And our website, the GDXP, also offer various tools by clicking the download image, um, which is not here. By clicking the download image button, we will invokes the WCS request, so we can let user to download the image by WCS. And if you just want to preview the image, we can use the WMS service, which you can click on the line title of the coverage. And if you click on the analysis button, which will open the WCPS template page. The user can choose different analysis method and parameters for analysis. They can also bring up template syntax and adjust it according to their preference before performing the analysis. And in our platform, there are various basic WCPS equation template are provide, including template for obtaining maximum, minimum, and average values of a specific image. Additionally, there are template for operations such as the binarization, the to binarize the image, and also the NDVI calculation, the layer stake, some useful tool for general user. For the image binary tool, user can set a threshold, and the data cube will binarize the image based on that threshold and create a binary representation between zero only with 0 and 1. And this is often used as an image mask for specific thematic purpose or to extract specific feature. And the NDVI templates allow user to select a satellite image source and manually specify the red and near infrared bands. And I believe you all quite familiar with NDVI, and we also introduced some NDVI applications in previous slide. And once the calculation is complete, user can download the result of the NDVI image, and also the layer stake tools that can let user to configure uh, the RGB visualization with compare with the spectrum band of the original coverage. And here are some WCPS basic syntax example. I I uh, I, I I didn't put too much, but just some example for you to understand how to write a simple WCPS. And this is the image retrieve process. So you can see the first line, we can define the coverage first by set the coverage name. And the second line, we define the scope, which is uh, the, uh, the bounding box uh, of our expect XY range, and also the uh, time parameters. Then finally designate the desired data output format. So with these three simple lines, you can get the image from the data cube. And for multispectrum, you can use the band with name to get a specific band. And this is the syntax that showing how we get the minimum, maximum, and the average value. So this part also be implemented on our website template. And uh, it shows that by specifying the image name for analysis and choosing the analysis method, which is the mean, max, and mean, along with the designated spatial and temporal range, the user can get the desired result. And also the layer stake is the quite similar. You can get the composition of the three spectrum bands. And this one is showing you how we integrate the WCPS in the QGIS. The GDXP WCPS requires an authorized token, which making it accessible in the native QGIS. However, there is we provide a solution through a QGIS plugin. Uh, once the user download and install the plugin and configure it within the QGIS plugin interface, user can input the required token and access to the sorry to the imaginary simulation. Okay, so here are some ancestry examples that uh, we can show to all of you. So in this example, we utilize the satellite imagery from two distinct time periods to compute vegetation index, which is NDVI, and conduct through a change analysis. So in the realm of the WCPS switch case, we will be tolerating the NDVI range and refining color patterns to suit our analysis need, and essentially fine-tuning the visualized representation, and simultaneously employing the WCPS scale. The WCPS scale is crucial for ensuring uniform spatial scale between the image from both time period. And consistency is key in this comparison. So we use these two processing to send to both images and get the result. So by examining the reflectance in red and near-infrared light, we can effectively unveil the health status of vegetation, which is here. Uh, this approach provides valuable insight into the overall well-being of plant life through the analysis of light reflection. And the image below, image on the right-hand side, uh, uh, illustrate the result of the vegetation index calculation by subtracting the two images here. The two images, we obtain the changes in NDVI. The darker area indicates an increase in NDVI value and suggesting an enhancement or increase in plant health or density. And in the other hand, a decrease in NDVI values, which is the white area, the decrease in NDVI values signify a reduction in vegetation or decline in plant health. So this we can use the WCPS to carry uh, this experiment by using the a very simple uh, code, write some simple code. We can do that. And this is the adjust image size, the WCPS scale that we mentioned. And in this process, we're reducing the image dimension to 1/10 of the original size, and we are adjusting the x-axis dimensions to 1000 pixel while maintaining the original uh, proportion in a y-axis. And this is the WCPS switch case that we also dividing the NDVI into 5 intervals and displaying each intervals in distinct colors. And this is the last page. I think we are moving faster than I thought, but we can have some time to discuss in maybe later. So that after the introduction, I want to let all the audience know that DataCube can be adapted for the data management, data access, and data analysis in cloud environment. We have some practical case that can prove that, and hope the data silo can be solved through a well-designed federation mechanism. And also data fusion will enhance the innovation and reduce the barrier to integration. And finally, a data cube, from our perspective, a data cube is essentially a database that designed for store a vast amount of remote sensing or other raster-based data. So apart from having robust infrastructure and software uh, to uh, to communicate with the data authorities and the sharing mechanism is quite important. So in Taiwan, NCHC and the Taiwan Space Agency currently play a very important role. They gradually promoting data cube technology and concept across various public sector, like the map mentioned. They assist in applying data cube for analysis and research. So if any of you have further interest in today's lecture or wish to explore collaboration opportunities, feel free to contact me. Okay, so that's uh, the lecture today. Thank you for listening. So since we still have like uh, 50 minutes, does anyone has questions?
Does anyone has questions? No? Okay, we thank you very much, Professor Hao, for teaching and Professor Zhou for hosting. And we end today's course.
Thank you.
Thank you. Please note that next week's class will be on Thursday, December 14. Please fill in the Google form and the 2-question quiz. If you have any other questions, you can leave it in the Google form or email it to me. I will pass your questions to Professor Hao. Thank you very much for your participation. See you next week.